It is officially past 11 Eastern, 8 a.m. Pacific. So good morning, good afternoon, good evening, everyone joining us from around the tinyML community here. So we're going to get started now with our talk. Really looking forward to the agenda that we have today. Not two, but three tinyML talks that are going to be really exciting, cover a broad range of topics. So without further ado, let's get started here. So my name is Davis Sawyer. I'm one of the co-founders of a tinyML company called DeepLight and the local chair for tinyML Montreal and also Toronto. We have a really burgeoning tinyML community here in Canada, so we're really excited to be able to share some local and also some speakers from abroad. Also, the community is joining us from Parker Zhang from Qualcomm and Kevin Favre of Toronto, LG Toronto. So really excited to be able to put this together for you today. Our first talk we have is Evolutionary Needs of tinyML from Liang at Qualcomm Canada. Our next chat will be from Brian Plancher on tinyML EDU, widening access to tinyML education and resources. This is a really awesome topic and also related to our third talk and some demos, I think, from tinyML for STEM from Greg Gage of Backyard Brains. I will be using tinyML for neuroscience in K-12. So this is going to be super fun. Let's dive in here. And again, thank you everyone for joining us today. First of all, I'd like to thank our tinyML Talk strategic partners, Aeon Devices, ARM, DeepLight, Edge Impulse, Emza Visual Sense, Greenwaves Technologies, Gravity Inc., HotG, Imagimob, Clicatech, Latent AI, Maxim Integrated, Micro AI, NXP, Prophecy, Qualcomm, Kixo, Reality AI, Renaissance, Rixen, SAP, Seed, SensiML, ST Micro, Stream Analyze, SynSense, and Sentient. There are additional sponsorships available, so if you're interested and want to join the tinyML community, get in touch with Olga. You can see her email here below. A couple of really exciting things, actually. So we're already kind of mid-January. We do have the tinyML Summit 2022. This will be an in-person event at the same location it was in the past at the Hyatt Regency San Francisco Airport, March 28th to 30th. Registrations will open this month, so stay tuned for that. And this will be an in-person event, which is super exciting. And concurrently, there is the tinyML Research Symposium. This is an open event. This is really a great chance to get up to speed and share what's happening in the research community here. So that will also be held at end of March. And again, sponsorships are available here. So in parallel, there is the growing tinyML communities on Meetup. You can join the link here below. As I mentioned, this is our first virtual chat from the Toronto group. Always like everyone staying tuned for when we can do more of in-person events. But tinyML is a global organization, can join here for anyone who's new. And then there's also the LinkedIn community as well. So also there is the YouTube channel. So all the talks from today and the talks from the past all go to the tinyML YouTube channel. This is an awesome catalog and resource of all the different topics that have been spoken about. And you can find that here at the YouTube channel. And the next tinyML talk, it will be just around the corner, January 18th, with Ashutosh Pandey from Infineon Technologies. The topic will be exploring techniques to build efficient and robust tinyML deployments. So that will be same time as usual, 8 a.m. Pacific on the 18th. So let's get started here. We have our first speaker from Qualcomm, Liang Shen. Liang Shen joined Qualcomm from AMD ATI as part of acquisition in 2009 and has been leading development of multimedia software components for Snapdragon products. He and his team have been focusing on AI processors and systems since 2016. Liang got his BSc in biomedical engineering and a master's PhD on image processing and pattern recognition with over 20 publications in journals and conferences. He worked on real-time signal and data processing algorithms and systems for radar, sonar, and satellites. He then led the development and successful commercialization of new generation communication systems with TTS and ASR. In ATI AMD, Liang was responsible for next-gen ASIC software and handheld software. While interested and enjoyed with all the products he involved developed, the most unimaginable one is cycling back to work on AI, his fantasy area allowing him to pursuing the dream of making IoT become the wisdom of things. Thank you, Liang, very much for being a speaker today.
Hi, everyone. Yeah, my name is Liang Shen from Qualcomm. And first, really thanks for tinyML committee to organize this webinar, and also especially Davis, Olga, and Parker to organize this session. Really appreciate this opportunity to talk here. And so interesting is when try to prepare this material for the presentation, and just want to see how really to provide some useful information to the audience, because the challenge is that this audience could be the variety, different background. Everyone may be looking for really different things. So anyway, just try to, based on last 6-7 years working on the AI processor, to see any what kind of content really may be useful for this audience. Hopefully, after these 20 minutes, some of you get some useful information from this talk. So with that, so we'll talk about three things. Start with some the efficient on-device AI, then followed by the ultra low power AI, and then discuss some challenging and directions. So as we know, the obviously it's good, as Davis mentioned, really this is also from tinyML Toronto session, and so this is good to mention. This is this current new AI wave is triggered by the 2012 by the group from the Hinton's group really started this new AlexNet for ImageNet classifications. And so the interesting is really this ImageNet, really the competition has been started 2010, and then you see this chart really at the 2010 to 11. It's really the classification error is really on the around the kind of 26 to 28%. This, by the way, this is a top 5 error, and you see that major improvement really in the 2012 is because of this AlexNet, and you see this absolute improvement by 10%, and relatively really almost 40% improvement. And really, since then, you see this continuous improvement year by year. Really, all these solution is based on the neural network-based solution. And the later in the 2015-16, you see keep improving. Also, relative kind of improvement is high, but really this is almost kind of it gets to kind of limit. So you see overall, you see in 10 years really improved by 10 times. The also really compared with the human, it's human is kind of 5% error rate, and then really this result already beat human being on that. So with this, it's really that's how really very encouraged results, and that's why this deep learning neural network-based solution become very hot and popular. And if we look at more deep for individual kind of typical popular model at a time, every year people come up with some slightly different new model architecture. And so as mentioned, the AlexNet is about, if you look at the size of the model in terms of number of the parameters and the computation MAC needed, you'll see this from like it's a very high, over 200 million bytes kind of the parameters to really to the computation can go to this 11 gig max, all those things. So you see this the overall trend. You see it's a large model size and a high computation cost, but this one get leading to a good accuracy. So obviously this if you want to this is good really for the research. Also you can run this the big computer machine doing those things, but how you really deploy those onto device different will be a challenge. And so in around 2017 and 2017 and 2018, and Google look at this and say, okay, maybe we should need to find out the paper to try to come for something to reduce the complexity of the model. So the key thing is at the time, this is the MobileNet V1, V2. And you look at the V1, V2, really it's the key idea just to you, instead of this normal convolution, which is very computational heavy, is changed to so-called depth of count. So basically they separated these to depth of count plus the pointwise. And the MobileNet V2 really it's continue using depth of count, but instead of they added this so-called inverse expansion. So here there's an expansion layer which do the one by one count with you expanded the input channel to n times more, so that then you can do this depth of count, and then they show this the accuracy become better, but with a small model, all those. And so with this, then you can see the result. Okay. So you can see this the time, even with this mobile network V1 V2 model, and running on this Pixel phone CPU, it is over for the mobile V1 is over 100 milliseconds, and mobile V2 is 75 milliseconds. And we all know really for dependent use case, all those things, this may still be a bit slow. So at the time, really, obviously, like many kind of semiconductor company provided this different SoC chip, and so Qualcomm, we do one of those really those at the time it's back to 2017-18. We have the so-called 8150 chip, and we provide a custom kind of component to kind of accelerate those neural network operations. So for the mobile network V1, V2, really you can get really kind of single digits, really kind of around 2 milliseconds. And the Inception V3 is about 10, and the V4 it's about 20. And the rest, you can see those. It's even with the most big network like a VGG, and even it's 28 or 33. This important is you can think of when people using this on the device for the use case. If you need, usually depends on the use case, you may need to say, want to get 30, the input data 30 frames per second, then you want to get kind of around below kind of 30 millisecond processing time. So that's really this to enable, with that really enable lots of customer to their new use case to take advantage of the power of the AI and the neural network based solutions. So so how we did that is really this just like a very as you know, like in the chip today, you will see SoC chip. There's a lot of people familiar with this the CPU, GPU, DSP, and obviously with this unique challenge in terms of computation needs, all those things for the deep learning based methods, and people now commonly call this kind of a neural process unit for the NPU. And for us, we call it internally, we call this, in public, for the tensor accelerator. So we call hexagon tensor accelerator. So in short, really, it's there will be a kind of a matrix of the computer unit, and come together with so-called TCM, which is title coupled memory. And obviously, you know that with the computation, you have this the data and compute you need to do. So in order to do this efficiently, you really need the both. And obviously, there's lots of different design, and usually you have a DMA to really get the data from external SRAM or DDR stuff. And there's a various way people can do. One is obviously using include a large memory, large TCM, so that really people thinking of when you have a model, you can fully kind of load it to the TCM so that you really can compute it efficiently. But there's a challenge with that is because when you the memory size also contributed to the size of the die, size of the when the die is large and the cost of the high, and also when the memory is big and the power usage is high too. So there's all those kind of compromise you have to do how to make sure this efficiency you can get the best performance and efficiency on those. For the HTA, we have very small TCM, but we have DMA to really to instantly fetch the data, all those things. I'll talk a little bit in the couple steps. And in addition, really, we do this parallel kind of it's 8-bit, 16-bit fixed point processing. So you know that when we do the floating point computation, it's much more complicated, and computation heavy compared with fixed point. And that's why that's another way really to improve and the efficiency of the computation. And the other is, important is really to be able to, as I mentioned, we have very small TCM. So how to make it sure to working efficiently is really, we have a parallel data flow and a compute flow so that you can really fetch small portion of the data, then you started computation, and in the parallel, you will keep fetching the data and then really the processing. So that's really, it's kind of fully kind of parallelized, so that you really get the most kind of efficiency on those. So obviously with all those, we did deploy those to all the customers using our chip. And this one really not necessarily show how we provide a solution, is just want to show this, the challenge really when you enable, the solution ready, and on the device, usually for us, for example, we have our own framework called Snappy, but in addition, obviously, there's a different ecosystem. So we have Android-based framework, and also we can provide kind of a more native interface, depends on different application framework we want to using. So we can have a different way to expose the functionality of features so that to enable the use case in a faster way. So in fact, this one will later touch a little more is in the tinyML environment models. This could be much more, even more challenging on that as well. So now I'll talk about ultra low power AI. So obviously you see this with this the capability, all those things, lots of use cases you see on the device today. The different based method is already used for those and running quite well. But why we need this ultra low power? So around maybe 2018, 2019, and people now realize that the custom become in fact more demanding or more educated in a sense. Really before, for example, this is just one example. Say usually people if you do the video super resolution using a new database solution, and let's say for 360p to 1080p, and so there's a model, and you can really do that. To inference time could be constrained to 5 milliseconds in a high performance mode. We call this a turbo mode. However, this one will be much more consume much high power. And then if you can running in a low power mode, which called low SVS, the inference time may become 4 times high. It's around 22 milliseconds. However, the really power consumption you can control it really below 100 milliamps. So sometimes this is much more critical because you really want to have a power efficient mode to really to meet your requirements. You think about the video, you said it's a 30 frame per second. So you align the processing overall, it's below 30 milliseconds. So it's good enough for that. So anyway, so that's people find that really not only you want to always using optimized performance, sometimes you want to optimize the power at target performance. So that's one kind of scenario. The other scenario is really there's a more and more different use case, so-called always on or low duration or long duration use case. So those kind of use cases now people find using the deep based method, some use case become feasible, some use case become better. And so some example really like always on speech recognition, always on sensor recognition, always on camera, all those things. And the other is really to the context awareness, and you can detect your environment and some audio enhancement, especially kind of noise cancellation. For example, in this this kind of the online meeting, all those things, right? You can really do noise suppression for the background, all those things. So in that really Qualcomm, we also have this. We see these things we develop. We kind of have the AI sensing hub, and so that you can really do those very ultra low power use case with AI enabled. so that really can get the minimum, best performance for the minimum power on those. But this, if you think about it, this slight difference is really this compare with the previous we said on-device AI we talked about. You see, there's all different requirements. For example, for the computing capability perspective, really, these maybe you only need kind of up to 1 TOPS. Compared with that will be 1 to maybe 100 or 50, whatever TOPS, high TOPS you needed for your model computation, right? And the memory available also, this memory usage, overall memory needed, it's below kind of 2 meg or 1 meg. It really depends on your model. And for the normal one, people using 2 to 200 megabytes of the memory needed. And also the power consumption. Here really talk about really single digits milliamp or below kind of 20 milliamp, but the other is really 2 amps. So that's a really different challenge on those these targeted space. And also, since if you really want to get this very extra low power solution, and you have to everything have to tie together. One is really the model should be lightweighted, and the inference framework also really should be low overhead, and also you have to be very efficient on the memory usage. So just this is really just show this solution. Usually for this, in order to achieve that, usually you may have 2 kind of one is off target, the other on device. And so if we talk about this off target, the reason you need off target is obviously there's a training model, and in order to efficient running or on your tinyML kind of AI hardware, you really need to do some massage to really do the model quantization, graph transformation needed to really take advantage of your hardware, right? And also the hardware really does a special kind of layout need, all those things you may do the processing for the weights and other stuff, compression needed. All those things you do this offline, so that when you move to the online to running this, it's a very efficient, easy to run. So without really take time and the extra memory usage needed. So when you really do the runtime, it's very simple, just init, apply, and execute and run. So that's all. So in addition, obviously, the other thing is with the tinyML people on device, sometimes it's hard to debug, right? So you can do is you should provide off-target tool for model verification. For example, you train a model, you want to know when you move to on the device, make sure it's working properly. But if you don't have this kind of environment, it's very hard when you push to the device, then things not working, and then you really have to know what's the problem, right? So usually, if you provide this kind of tool, offline tool, you will be able to run these things from your trainer model, go through the model builder, and then really running it with this hardware simulator. So the results will be better exact match when you're running on device. So that with that, really when you move the device, it's really seamlessly do that. So with that, really just quickly to look at like all those things seems working, but there's the challenge we're facing. For example, also we want to make sure tiny but not but still generic and customizable. What that means is, as mentioned, is that there's a different ecosystem, different framework. Everyone, if you move to different tinyML platform, you may have to learn different framework, or you have to adapt to, right? So maybe it would be great, really, we can have a really common generic tinyML framework, but customizable, so that really be able to learning curve will be much easy, and also still maintain really very compact the solution we have. And obviously the tool, as I mentioned, are very important. And if we can make the tool more intuitive and easy to use, so that really people can easily adopt that solution. The other is, although we're tiny, but to make sure there's not compromise the quality. And obviously there's the size-wise, there's two fronts. One is the model size, And the model really people can use in all different so-called hardware-friendly training, hardware awareness, and the take advantage of sparsity, low bit position, all those things. So it can really reduce the model size. And for the activation, obviously you can do the compression, and also you can control the execution flow. What that means is really in the model, this different activation, the layer output. Some layer has a large activation size. So if we can bypass that, not the output intermediate in that level, could help you to reduce the size. And the last but not least is really tiny, but you can learning too. So really this, especially on device, all those things, if you can do some refinement, continuous kind of improvement, also personalization, it will help make the solution better. So with that, just to finish it, this just using this the quote from Jeff Hankins' book called "The Thousandth Brain," a series from the Thousand Brain. Basically, accelerated brain creates a predictive model. This just means that the brain continuously predicts what its input will be. Prediction isn't something that the brain does every now and then. It's an intrinsic property that never stops. It serves an essential role in learning. When the brain prediction are verified, that means the brain model of the world is accurate. A misprediction causes you to attend to the error and update the model. Obviously, everyone does a different, nobody knows exactly how brain works, but that's one way to kind of interpret that. But I think hopefully this can guide us to make, using tinyML to make a device more intelligent. Okay, that's all I have. Thank you.
Awesome. Thank you very much, Liang, for that interesting talk. That was a great review of the evolution of tinyML and the different needs and requirements that are still evolving. So thank you very much for taking the time. So with that, we'll dive into some questions here. So one question here is, are there tinyML runtime libraries optimized for certain SoC like Qualcomm SoC, so that the available hardware architecture is used in the most efficient way for inference? So that's one of the first questions here.
So again, the question, yeah,
sorry. It's the, let me restate that. Sorry. The question is, are there tinyML runtime libraries optimized for certain SoCs like Qualcomm SoC so that the available hardware architecture is used in the most efficient way for inference? This is a great question.
Yeah, I think I understand if I understand the question correctly. What it means if we have using our framework and then we have all the different chipsets, right? So that will run automatically efficiently for different chipsets. It is true, yes. It's because as you see in one of the slides showed, underneath there's a different version of the library to specify for different chips. Also, our hardware is evolving, right? So those libraries will take care, automatically detect which chip it is and take advantage the best for this version of the hardware.
Awesome. Yeah, that's a really interesting question there. And kind of, I think, related to this question, another one from the audience is, which tool suite for evaluating quantization and measuring the hardware performance values? Which tool suite do you use when evaluating quantization?
So there's a different the tool we have, and I think if we talk about the tinyML, the ultra low power one, as I mentioned, in one of the slides I did have a link. So we have a SDK you can download, and in this we have a tool, basically a complete offline tool you can run it on the Linux. And with the hardware simulator, just run through that with the model. You can do the quantizing and check the quantization results, match your expected golden result.
Cool. Actually, a follow-up question I have to that actually is, how do you manage any retraining you have to do in this hardware emulation? Like perhaps you can estimate a model performance as is, but if you have retraining, which might be the case with quantization, how is that managed?
You mean the training?
Retraining of the model.
Yeah, so basically the flow you see in the left side, basically you figure out if it's the result match you or not. Then if not, good, right? So then the number of possibility. One possibility is the quantizing parameter is not good, so you can refinement. Okay. Qualcomm does have a tool called ARMAT. It's open source as well. You can go that. Then there's a way you can do this to mixture of quantizing properly. The second one is obviously you guys know that some model may be not quantization friendly. For example, the original MomoNet V1 is not quantization friendly. And in fact, we had a paper to change the model architecture, so make it hardware kind of quantization friendly as well.
Cool. Yeah, that makes sense. And actually, thanks, Parker. So in the chat, the link to AI Met that Liang just mentioned, that's also there. Yeah, so please, any more questions? And again, if they don't get answered now, if you think of it later, you can put it in the chat still, and it'll be put up in the forums. One quick one before we go here, and I think it relates to the quote you gave, which is really awesome from Jeff Hawkins' book. In the context of tinyML, you know, one of the ways you can think of the brain updating its model is on-device learning. So I mean, and there's many concepts out there. I noticed it was not to maybe explicitly one of the trends here, but how do you think of that? And also from a hardware perspective, what's possible? What do you think of tinyML constantly constantly running?
To me, that's why I really believe in the coming. I believe in 1 or 2 years, you will see people starting moving the training onto the device. This training is not from scratch, because not necessarily needed from scratch, but it is a refinement, updating of the model in the device. This again will be also great option for the chipset vendor really provide this capability into that. So I believe this is a trend. It's just a matter of the time.
Cool. That's awesome. Yeah, we're getting. I think a lot of people feel that way in this community. So one last quick question before we get on to Brian. This is for you, Liang. So the question is, from the hardware perspective, how is hardware-aware optimization training done? This will be the last one we'll do live, and then we'll move on to the next talk here.
Yeah, there's a number of things that's a thing is because we need to provide you some hardware information to do the hardware-aware training. So we're looking at a thing in the AI Mat. We try to plug in more models information in that, so that customer can using this to do the hardware-aware training. So stay tuned. You will get this information from the AI Mat.
Okay. Awesome. Thank you. And thank you to all the strategic partners. And again, there's also additional sponsorships available. First of all, you know, so the executive strategic partners of tinyML, you have ARM, the software and hardware foundation for tinyML, Edge Impulse, the leading Edge ML platform, Qualcomm AI research, advancing AI research to make more efficient AI ubiquitous, sentient neural decision processors, end-to-end deep learning solutions for tinyML and Edge AI, and to the platinum strategic partners, DeepLight uses AI to make other AI faster, smaller, more power efficient, from software to runtimes. Klikatech Global IoT Solutions. Reality AI, add advanced sensing to your product with Edge AI tinyML. Renaissance, broad and scalable edge computing portfolio. And to the gold strategic partners, Maxim Integrated, enabling edge intelligence. Latent AI, adaptive AI for the intelligent edge. Also Micro AI, NXP Semiconductors. Seed Studio, the IoT hardware enabler. SensiML builds smart IoT sensor devices from data. ST Micro, life augmented. SynSense builds sensing and inference hardware for ultra low power embedded mobile and edge devices. And to the silver strategic partners, Aeon Devices, Emza Visual Sense, Greenwaves Technologies, Gravity Inc., Hotg, Imagimob, Kixo, Prophecy, Recent Technology, SAP, and Stream Analyze. So the next talk, again, right around the corner on the 18th, 8 a.m. Pacific, 11 Eastern, we have Ashutosh Pandey from Infineon Technologies, talking about robust tinyML deployments. And with that, I'd like to thank everyone for making this a really fun, really successful first talk from tinyML Toronto. Keep in touch for more groups, getting involved in the community, joining the meetup groups, YouTube. Everything's available online. Thanks again to the speakers, and wishing everyone a great day.